Okay, so this topic is prepared by Francesco, my colleague in Europe, and I'll present for him. So we're talking about the mythbusting for the commonly used EMI reduction technique in the power converter designs. So the purpose of this topic is, we see on seminars, on articles that people recommend the EMI reduction technique or tips, right? And we do find sometimes it's working, sometimes it's not, and sometimes it's work for this case but not for that case. So we try to build an experimental, comparison to see for some techniques is working for this case or not. So it's more of an experiment comparison, but if you want to get rid of that, look at my previous slides that we're talking about how to analyze the EMI, then you have more confidence what you're doing. So the method we use is basically we pick a board and pick our IC, and we do the layout. We do different layout, but each version we only change one thing. So we'll see if that specific change is going to change the EMI result or not. And here's a circuit. We take 43 XX family. This is a 3 amp buck monolithic buck 40 volt for automotive case, and we have the EMI filter in front of it. So we're using this board for the comparison. And for the testing method, it's follow 6x25 standard. And for the output, we just connect the resistors there to emulate the typical motherboard applications. So first case, it's about the symmetrical input cap. So the idea here is if we have our reading covering cap on both sides, then this so-called hot loop, the high DIDT loop, is generated in the opposite direction, and hopefully it can cancel the EMI, when it's coupling around, right? And let's see if this is real or not for this specific board. So we prepared 4 flavors of the layouts, and essentially the same layout, but we just place the cap, the input cap at different places. For the first case that we place the input cap symmetrically, you see there's a big cap and also smaller cap. And for the second case, we simply remove the smaller cap, but the big cap is still arranged in a symmetrical way. For the third case, that we remove all the cap to one side, so no more symmetric, but the overall capacitance is still same, so the same capacitance value. And for the last case, it's a symmetric, but it's only big cap. We remove, it's unsymmetric, asymmetric, but only with the big cap on one side. Just no small cap. So compare the 4 cases, the EMI result. So here's a comparison. So you can see that the green curve, which is the symmetric case with the smaller cap, 100 nanofarad cap, is a winner. It's a lower frequency above, start from 40 or 50 megahertz, its noise is much lower. And before that, it's similar, right? So this is conductor EMI average measurements, and we compare from 30 megahertz to 110 megahertz range. The second place is the symmetric say-in removed. So you can imagine that without the smaller cap, and your total ESO is slightly larger than the first case, so the high frequency performance is slightly worse. But looks like the symmetric cap still play its role, right? It's helping. And for the third case, it's without it's asymmetric cap, but with smaller cap. So it's worse. So basically it's saying same capacitance value, but if you don't have the symmetrical result, is worse. And for the reason I think I explained in the last presentation, when there's noise cancellation, another thing is you also effectively reduce your ground impedance by pairing these two ground together. And for the last case, as you can also tell, without this smaller cap and it's asymmetric, this is the worst case. And also let's look at the rated EMI from 200 MHz to 1 GHz. Actually, this case, it's much harder to tell. You can see some frequency range symmetric is good, and some frequency is not that good. But what you can tell is a smaller cap always helps. This 100 nanofarad is always help for the case. Okay, so this is for the rated EMI. And I think to conclude for this case study, we think for this case, the symmetric layout definitely helps, and also the smaller cap will also help for the higher frequency. So we confirm this is a myth-busting. This is a real. This is true for our design case. For second case, let's talk about the ground plate splitting. So this idea is based on the theory that if you have high frequency current and you have a huge ground plate, then the current is spread out, right? It might go to your edge of the board, it might go to your sensitive components of the ground, so that make your sensitive components noisy. For example, you have EMI filter there, then you don't want the EMI filter's ground be noised by the spread out current, and you have accurately op-amp there. You also want to the op-amp or the ADC's ground is accurate, it's low noise. So the idea is if I shape that ground, then I can contain this AC current just within this island, and then I'm sure outside this island the ground is clean. So let's see the experiment. So we did 4 layouts for this case. The first case is we have island on top and also on the P ground, and we also have the island on the inner ground. So we basically shape all the AC current just in a certain area. And for the second case, for top layer in P ground, we still have island, but for inner layer, there's no island. It's just go everywhere. And if you think about it, you might think, okay, because it's inner layer and it's shielded by both top and bottom, maybe not that's critical, right? And this is the result. And the third case is we have only power ground has a cut, but on both inner layer and top we don't have a cut. And for the last case, there's no cut at all, so all ground is connected together. And let's see the comparison. So here is again conduct EMI measurements for this full case from 30 MHz to 110 MHz, and you can tell there's not much difference for all those full cases, all pretty similar. And let's look at the rated EMI. So this is from 200 MHz to 1 GHz. And in most of the frequency band is also pretty close, but for some frequency band you can actually find the all cut case is actually worse. This kind of contradicts to our goal, right? Our purpose when we design this island. So why this happened? So I'll talk about this a little bit, but I won't dive in too deep. So reason is this technique will be effective if you do have a huge amount of AC current that spread out widely to your sensitive area. But for this board, we actually run the simulation of the current distribution. We see the current distribution actually is not even reached to the edge of this island. So that means it doesn't matter you have the island or not, the current is pretty much is just contained there, right? It's just small pound of a current. So that's why, you know, this technique didn't help, and why in some frequencies it's worse, because you do have the little drawback of this technique. When you isolate the ground, or you make this island, then this gap between the island ground to the outside ground, it actually has parasitic cap, and this cap in the high frequency, you know, might start to coupling the noise around. So this is start to pick up at a high frequency. It really depends on your design again. So you have to really run the simulation and to see where it is going. So basically, you can see, you know, the technique that proposed here is useful for some cases, but actually not useful for our case. So this again, you know, this myth actually will consider is busted. It's not true for our case. But you see how this process is going, right? If we're just using this practical way to judge and to think, I can reduce EMI this way, or I have a good EMI reduction technique, it might not be true. And if you really want to get a bottom of it, you have to analyze, understand it, and quantify it. So, and that way you can optimize your design. Okay, so for the conclusion for this experiment case study, that we can say, basically we started two cases. One case that is we're talking about symmetric layout and is effective, and we talk about the split ground, and unfortunately in our case that's not helping, but you know, in other cases it probably helps, right? So it depends on the design. And yeah, our suggestion is, you know, if you don't know, then you need to really simulate it. But if you do have very similar board, or your design is very similar to the previous case, and your rating, current level power rating is also very similar, then those techniques probably will hold true. So you need to understand the boundary, how you're using it, and you know, if you go beyond the boundary, you need to look at it another way. Okay, so this is my presentation today, and questions.